Good evening. We have several show and tell sessions this evening. Unfortunately, the first one, Bill, due to his some personal issues, won't be able to make it. But then we will have Tommy on astrophotography. Tommy, be ready. You are going to be the first. Joe will talk about Maker's special interest group. Dustin is going to talk about the meteorites. Then we have two projects from SETI, Ed and Augie. And then I'll finish with talking about a comet that we had last month. So, Tommy, are you ready?
I am ready. My name is Tommy Lease. I'm one of the ASIG or Astrophotography Special Interest Group leads. Myself and Greg Fogarty lead the ASIG. I thought I'd put together a quick little presentation on, basics of astrophotography, how to get started in it. So tonight's topics, first we'll start off with what is ASIG, and then we'll talk about tracking the stars, and then telescopes, cameras, and tracking mounts. And then we'll talk about stacking images, DSO and planetary. Then we'll talk about post-processing, Q&A, and example imagery. So what is the ASIG? So ASIG, or Astrophotography Special Interest Group, was originally created by Joe Pineda, who is doing the MakerSIG now, and also Greg Fogarty. This was created due to an increasing interest from other DAS group members on imaging the night sky. So we focus on helping others with their equipment, hardware, software, and also processing their images. So the ASIG, we're currently at, I believe, 265 members and counting. As of right now, we meet 3 times a month via Zoom, and also do some dark sky meetings as well, both at the Klein Dodge dark sky site and the, what is it called? Sorry, down there in Larkspur. But yeah, we meet in both places. So yeah, like I said before, the meetings are hosted by myself, Greg Fogarty, and Charlie Hagan. Charlie hosts the advanced post-processing meetings. So we can be reached at the email that you see there on the screen, or we also have a Slack channel, hashtag astrophotography. So tracking the stars. So why do we track stars? So star trackers are important for astrophotography because they allow cameras to track the Earth's rotation, resulting in longer exposures and more detailed images. So without a star tracker, a camera and a tripod can only take an exposure for around 30 seconds before the star trails start to appear. Long exposures produce more detailed images, detailed and colorful images. So talking about telescopes, cameras, and tracking mounts. So there are many different types of telescopes, cameras, and tracking mounts, and also the accessories that go along with them. So why are there so many types of each? They all serve different purposes. For example, star trackers and equatorial mounts, combined with faster telescopes and lenses, work great for imaging targets such as nebulae and galaxies. On the other hand, you can have slower telescopes such as SCTs, MAC-CASs on alt-azimuth mounts, and these are great options for planetary imaging. Then you have different types of cameras that can range from DSLRs, dedicated astro cameras for DSO, and also planetary cameras. So talking about stacking images, both with DSO and planetary. So why do we stack our images? The main reason we stack our images is SNR, or signal to noise ratio. The more images we stack, the better the SNR is. This equates to more detail and less noise in your images. As for taking video, this generally applies to planetary. This is also called lucky imaging. Now, lucky imaging is a technique for capturing planets and DSO using CCD and CMOS video camera and software to sort. You can use sorry, screwed up on the slide there, but you use different software to sort the quality of your images. It involves taking thousands of frames in high-speed video and then sorting the best frames into a final high-resolution image. When capturing images of planets and our sun, you want to get a bunch of short exposures or video due to how bright the planets and sun are. So post-processing. So why so many post-processing programs? Well, it goes back to serving different purposes. For example, a program called PixInsight is used mainly for DSO stacking and processing. Then you have programs like Registax that's used to stack and process planetary images. Then you have programs like Photoshop and GIMP that were developed for landscape and portrait photography, photo processing, but you can also use these for astrophotos as well. So next we'll take a look at some example imagery. So on the left here, left and right, you have two examples of narrowband images. On the left, you have the Rosette Nebula, and on the right, you have the Pac-Man Nebula. And then we look at some broadband examples, two galaxy images. On the left, we have the Whirlpool Galaxy, and then on the right, we have M106 and NGC 4217. And then we have some planetary examples. On the left, we have Jupiter, and on the right, we have the sun. Does anyone have any questions?
He doesn't do much planetary photography, does he?
No, I don't.
How sure are you that that's Jupiter?
I'm pretty dang sure.
Maybe you should look at it again.
That's Saturn. I see why you guys are laughing. Sorry about that, Greg. Oh boy, I need to get more sleep.
I am Joe Pineda with the MakerSIG. Can you guys hear me okay? So tonight I'm going to show you what I've been working on since April to the exclusion of everything else. What I have in front, I don't know if you can see it, I hope you can, is a 8-inch Newtonian reflector telescope that's entirely 3D printed except for the glass, the mirrors, the glass, and a guide scope that comes with it, and a motor and temperature sensor, coupler, and 4 carbon fiber tubes. Everything else is printed on a Bamboo Labs X1C printer. The scope design is a f5.9 8-inch scope. It has a 60 millimeter secondary mirror designed for with a 55 millimeter back focus that's yet to be measured. It has an Arduino Uno R3 electronic focuser using a NEMA 17 stepper motor drive and temperature sensor included. And it's got 120 lines of embedded C code for the Arduino. So it's pretty simple. It's designed for astrophotography. And the entire thing was designed, including the guide scope, using AutoCAD or Autodesk Fusion 360. It has a plastic to metal interface at the focuser using a flange for either M48 or M54 threads. It includes the 73 millimeter f3.8 guide scope that we had last year. That's sitting on the top there. And the tubes are 1,200 millimeters long and by 26 millimeters in diameter. They're carbon fiber. And the design calculations I got for the scope from this website I have here, it makes it real easy. It makes it like almost cookbook-like to design. Portions of the tube come from a guide scope focuser design. The alias is Balinux at printables.com. And also let's see, and the cost to build the focuser, the tube, and the guide scope, and the dovetail, all here, everything you see in front of you, was about $600 so far. I'd like to get that price down once the design is finished. The weight of the focuser, the tube, the guide scope is currently 13 pounds, and I think I can bring it down 3 pounds, going to a slightly different design. I don't know if you guys can see online, the little boxes at the front and the back and the middle weigh 2 pounds, and thank you. The design is going to go to this circular design, which sheds a lot of weight. So this, what you see before you here, weighs just under 1 pound. So with three of, huh? Okay. Okay. So this weighs 1 pound, and what you have on the scope already is 2 pounds each. So I'm going to bring the weight down with that. Let's see. So I have a demo here for the focuser. I'll save that to the end because that way we won't have to switch around. So the planned work for the next 6 to 9 months, reduction of the mirror cell, center body, and diagonal section overall weight. The addition of an insert for a laser collimator. Thank you. I looked at using custom carbon fiber tube links. It's too expensive. I'm just going to use what I have as is. Reduce the size of the stepper motor for both the focuser and the addition of a flat panel motor-driven cover for the front is going to go from NEMA 17 to NEMA 11. It's a smaller motor, weighs less. And develop NINA astrophotography software plugin instead of writing a device driver for the focuser. That should make it easier. Field tests and then mostly testing. I've got a Bader coma corrector, blue fireball manual rotator, and some ZWO stuff to make it an AP rig. Improve the cable management, embed the cables inside the structure of the scope itself, and add a new design for the motor-driven flat panel cover, which I mentioned. And once it's all done, publish the whole thing on printables.com. And that's really all I had. This is some of the pictures of the AutoCAD design. Those are the 3 major sections, and then the guide scope at the bottom. And there's just a close-up of the diagonal section. So a lot of 1,000 little tiny details to make this happen. So what I'm going to do now is I'm going to demonstrate to you guys. Those of you in the room will be able to see this better. The focuser. So in order to do this, I have to type on the keyboard here. I kneel down so you can see. So this is Arduino IDE, the integrated development environment for the Arduino Uno, which is right here, where this little thing here is. Am I in your way? Okay. And so what it will do, the way you control it is you type the letter T as a command, hit return, and it tells you the temperature in centigrade and degrees Fahrenheit. And then if you type, say, D or display, it displays the current position. The focuser goes from 0 to 65,535 steps for full extent. It's currently at max focus out. So this is the focuser here. And so I'm going to focus in by half. Let's see. I'm going to say G for go. G, 3, 5, 5, 30, no, I'm sorry. 32, 7, 6, 8. It's a little bit noisier than the ZWO focuser, but it does spin.
That's good.
Yeah. The reason it makes noise at all, if you don't put any load on the motor, it doesn't, you can't hear it. And I think what it's doing is transmitting vibration through this shape, and that makes the sound that you hear. The reason for not using the ZWO electronic motor is there's a gear reduction transmission inside it that causes it to be too slow for this application. So I just went and did my own. And there you have it. Any questions?
Thank you, Joe.
Oh, you're welcome. If you want to come see it, it's impossible to show everybody at once. The main mirror is back here. You can just come up and look at it later at the end of the presentation. The subreflector is right up in here. And this is a refractor. This is the guide scope. The whole thing 3D printed. Thank you very much. Yes.
What was your total print time? Total print time.
Oh, each one of these takes 15 hours. Each one of these sections, 15 hours. The printer was this piece. Oh, yeah. So this piece is what I'm going to go to. 15 hours for this. These too big, 22 hours. Yeah. So you save a lot of time and money and plastic weight. So the way to improve it. Anybody else? Thank you.
How many times do you have to reprint all those parts?
Say again, please.
How many times have you had to
It's a Bamboo Lab X1C printer. It's Flash Forge ASA filament, which is a high temperature weatherproof filament. So that's all of this is that. And I had to do, someone online asked how many times? A lot. I have a lot of busted plastic on the floor in my garage. So it was interesting.
I'm not surprised.
I didn't catch the online question, but I believe that was what it was.
Yeah, that was it. I just said I'm not surprised.
Yeah. Yeah, just learning Fusion 360 took forever. So,
Joe, this is Tommy.
hey, Tommy.
Hey, you know I'm a sucker for the Newtonian, so I may be placing an order with you soon.
I'll make one with your name on it. Or
Thanks.
whatever name you
Nice.
choose.
Yeah, nice work on that.
Thank you.
Overall, how much time have you put into this effort?
Since April, like 3 to 4 days a week. And most of it is just like learning AutoCAD and, getting it right and measuring all this stuff out, that sort of thing.
How is the SIG working?
Not so well. It's a large barrier to entry to get people to want to spend this much time building something. And then there's the cost of the printer itself and all that sort of thing. So I think you can't schedule breakthroughs. So basically what you should probably do instead of having a monthly meeting is wait till you reach a milestone, like a real engineering program would have. You have a preliminary design review, critical design review, and then you have a test, readiness review, and you do field tests and you do all those things. And that might be a better way to go rather than, yeah.
Okay. Well, thank you.
Hi, I'm Dustin Dickens. I'm the director and manager of the Laboratory for Meteorite Analysis and Classification, formerly the Colorado Center for Meteoritic Studies out of Loveland. And we do most of our analysis at the Electron Microprobe Lab at the University of Colorado at Boulder. So obviously this is going to be a bit of a departure from astronomy in stricto, as we're talking about the physical planetary materials that actually show up here. This presentation is going to be very quick, and I'm not going to get too deep into it. So I really took the idea of show and tell quite literally in this case. as I suspect most of you are probably not too interested in me getting into the nitty-gritty details of the geochemistry and petrology of these things, as opposed to just kind of giving a brief overview of what they are. But one thing I did want to get across at this presentation, if at all possible, is that these meteorites are pieces of larger asteroids and planets. And so there's a reason we study them. And there's also something else that's very nice about them, is that they're a lot cheaper than return missions. We essentially get free samples delivered directly to us. And as a result, it offers a lot of opportunity for research and for understanding the planetary bodies that exist in our solar system. And so again, the one takeaway I would probably hope that everybody gets before I just start sort of picking things up and telling you about what they are and the names of them, is that these are pieces from larger asteroids and planets, aka parent bodies. And we do oftentimes know what parent body that they originate from. Well, I wouldn't say oftentimes, we do occasionally know where they come from. And then sometimes we can just surmise roughly where they come from in terms of, are they from the inner solar system, somewhere between, say, Mercury and Earth? Did they perhaps form from the the protoplanetary reservoir that Earth formed from, in the case of the instatite chondrites that I'll talk about and show you in a moment. And really that's about it for that. So the ones that we do know about, where we're almost real confident that we know where they come from, are Mars, the Moon, Vesta, and or the Vestoids, which were at some point liberated from Vesta proper, when it was probably more of a planet or a rounder planet proper at some point, at least based on some models and some theories. And then there's some others that, based on geochemistry and on the petrology and the isotopics, again, like I said, we can surmise that they probably formed somewhere close to Mercury. In some instances, we might have some ideas that they may have actually formed on Mercury. There's a lot of debate as to whether or not that's true or not. With the Aubrites, some of these new ungrouped chondrites that I've been studying and that I'm most interested in, there's at least the possibility still that they may actually be from Mercury, although that's very controversial and not in any way well established. And then, of course, there's also the carbonaceous chondrites. And these carbonaceous chondrites have amino acids, prebiotics, and at least in one case, an actual full protein. And so to a large degree, we feel like potentially a lot of the water that may have been delivered, and I should have mentioned that some of these carbonaceous chondrites have as much as 40% water or hydroxides in them. And the minerals, the minerals that exist in them have to some degree, depending on which meteorite we're looking at, may have been altered into these hydrous phyllosilicates by as much as 30, 40, 50, in some cases 80 or 90% of the minerals have been soaking in liquid water endogenously in the asteroid that they came from, out in space, not on Earth. So there's a lot of water out there. And so anyway, we can then surmise that these particular carbonaceous chondrites, I'm holding one up now, I have some pictures that'll come later in the slides, that these guys were formed, at least 4.5 AU out into the solar system where water ice can form. And during the accretion process, it can be incorporated into the asteroid. And so without much further ado, I'm going to essentially just sort of run through the meteorites that I brought for show and tell, and hopefully the images for y'all at home will suffice And for those that were fortunate enough to show up here, or be able to show up here, I have them physically sitting on the desk in front of us here right now. So the first one is an instantite or an e-chondrite. Pardon me, I lost the T and the E on that one. This is from Morocco. The name is NWA or Northwest Africa 15893. And this is it, holding this up right now for those of you here. And this is one of those meteorites that we talked about that might possibly come from a lot closer to the sun and or around Mercury and or perhaps into the Earth zone. But the instantite chondrites are undifferentiated, come from undifferentiated planetary bodies. And so what that means is that it never got so big, and gravity and heat didn't alter it. And so we still find these little globules called chondrules, and meteorites can be separated into roughly two types: those with chondrules, chondrites, and those without chondrules, achondrites. Most of what I'm going to be showing you today are achondrites, just because they're the most interesting for me, and it's also one of the ways that we know what planetary body they came from, because they came from these large bodies that went through differentiation. And so I hope there's not too much jargon here, but I'm keeping it at the bare minimum, I promise. So another one of these inner solar system meteorites called the Augies. These are, again, lost the T, the E on the end of there, apologies. This is from Mali, and this is from a differentiated asteroid. Some argue that it could be from Mercury, and I won't get too much into why, but some age dating has, for most researchers, has precluded the possibility that it was from that. However, it is almost certain that it was formed near the orbital zone of Mercury, based on some of the sulfides, these particular minerals that we find in them that have to form in an area where there is just no oxygen and really there really are no other places in the solar system that have the kind of heat that would get rid of the amount of oxygen and allow for these sulfides and for these minerals to form in the way that they did. And this is also true for these new ungrouped chondrites that we've been finding over the last few years. They have very similar geochemistries and properties as the Augies and even these echondrites. However, they're mineralogically very different, and they have some very specific minerals, these sulfides I was talking about, that make it even more likely that they may come from Mercury. Again, very controversial. One of the reasons I can still say this, whereas I really can't say that so much about the Augies, is that we haven't done the age dating, and this essentially on this yet, at least not that I'm aware of. And what we find when we do this age dating is that for the Augies, this other large differentiated parent body that the Augies come from was older than what we suspect the crust of Mercury to be. So therefore, it couldn't have come from Mercury if it formed before the crust of Mercury formed. So anyway, these are the inner system meteorites, and there we go. And so let's move on to some core forming meteorites, or a core forming meteorite. So this big 30 something odd pound, I should know my conversions better, but 13.3, I think in kilos and grams now. This 13.3 kilo meteorite is what formed a meteor crater in Winslow, Arizona. And it is essentially it's a piece of what we have in the core of Earth, in the core of every rocky planet that's gone through the process of differentiation. And the only reason that we see it here is because the parent body of this was cataclysmically destroyed in some huge impact, and it liberated the core material and ended up here on Earth. And one of the ways we recognize it immediately is that when we do some just even basic X-ray fluorescent analysis, XRF analysis, we don't even really have to get into the microprobe or the more the more accurate ICP-MS types of analysis is we can see immediately it's got a very distinctive iron nickel composition. And all of our iron nickel is sequestered at the core of our planet. And so it's a really good indication that you found a meteorite if the composition is made out of iron nickel and some particular ratios. And so probably something that you all are a little bit more interested in are these meteorites that we're almost certain come from Vesta or the Vestoids, and this is based on remote spectral data. We haven't actually physically taken any samples from Vesta yet. But this is called a eucrite. This is the E in the HED. H stands for howardite, which is a mix of the E, the eucrite, and the D, the diogenite. So here's a diogenite, which is right here. Pop this out real quick. These are not so delicate. So the diogenites are believed to come from deeper down in the mantle of Vesta. The eucrites, which is right here. And I'll go, let's see if I can find. So this is the picture of a eucrite here. And these guys are from the crustal material, or thought to be from the crust. And so when they get a giant impact, this is also a bigger piece of it. This is a breccia. And you can see that there's just basically fragments or chunks that have been blown apart and then reconstituted, which is what a breccia essentially is. And this is just another version of the eucrite. And to create a howardite, the H, just blow apart a bunch of area, dig real down deep, and then throw them back together in a breccia, and you've created a howardite for the HEDs. And so that's Vesta. Now, even further out, we were talking about these carbonaceous chondrites that have as many as 90 amino acids, many left-handed amino acids, prebiotics, alcohols, and a substantial amount of water. There are many, many types of carbonaceous chondrites. This is one that we're currently classifying right now at LMAC. This is most likely one that's called a CM2. The 2 is an indicator of how much it's been aqueously altered. The C ungrouped is another possibility. And until we get oxygen isotope analysis back from our colleagues at the Open University, Dr. Richard Greenwood, we won't really know whether or not it's a CM2 or a CN grouped. And essentially, we just need to have the oxygen isotopes plotted, and that will tell us roughly where in the solar system it formed and whether or not it plots to the already known CM2s, or if it plots somewhere completely different, which then makes it ungrouped. And I should note that ungrouped does not mean unclassified. Ungrouped just means it doesn't fit into one of our existing taxonomical areas. So there are quite a few, more and more now, of these meteorites that we're finding that just don't fit into our historical classifications. And then finally, something we can all relate to is a piece of the moon. This is a lunar meteorite that, I don't know if you can see this, but that broke my saw just 2 days ago. And so I'm waiting for my new saw to come in so we can finish taking this piece off. This is what's known, we used to classify them as feldspathic breccias because they're primarily made out of a feldspar, a high calcium feldspar or plagioclase called a northite. More recently, we've been a little much more strict in following protocols, and we're starting to call them fragmental breccias. But either way, it's pieces of the highland of the moon. And the dark spots, the dark areas are not the mare basalt parts. They're actually just shock darkened versions of the same light feldspars. And this is my favorite one. This is from my personal collection. It's I call it the pigeon poop meteorite because it really just looks like a piece of bird poop to me. And I mean, in a good way. And it's just, I don't know, I just find it to be a particularly aesthetically pleasing piece, despite my nickname for it. And there's another lunar meteorite here, but I'll let you guys come up. So the idea is that for show and tell is that these will all be here for you guys to come in and look at and hold and ask questions about. And then finally, I probably well over my 10 minutes, but finally, probably the ones that I was most interested in at first and that most of my previous research and diagnostic time was spent with Martian meteorites. This one is a very famous Martian meteorite that fell in 1962 near the town of Zagami in Morocco, and it's a Martian shergotite. So, not to get into too much nomenclature or jargon, but you may have any of you that pay attention to this at all may have heard of the SNC meteorite Martian group. Stands for shergotite, knocklite, and chasignite. This is the S in the SNC group. It's the most common of the Martian meteorites. However, this particular Martian meteorite is particularly rare because it was seen to fall. Most of the meteorites that we find today, that we have to study today, haven't fallen, but we've found them after they've fallen. And so these Martian meteorites, in fact, we've never seen a lunar meteorite fall. Every lunar meteorite that we've gotten has been one that has been found after the fact. So anyway, that's it. I'm going to do a shameless plug if anybody's interested in having a meteorite classified or suspected meteorite classified, they can go to our nonprofit research website, meteoritic.com. And our for-profit, if anybody's interested in actually owning one of these or as a collector of meteorites, most of the money that goes to support the Laboratory for Meteorite Analysis and Classification comes from our retail at topmeteorite.com. We also have jewelry if anybody's interested in having a piece of the moon or Mars or a chondrite. And that's it. Thank you very much. And I invite you to come up and touch and hold and interact with the meteorites and ask any questions you guys may have. Thank you very much for having me.
Thank you.
Questions, yes. Oh, absolutely. As long as I have time, sure. Yeah.
Oh, I'm sorry. Yeah, I'm fascinated by the finding of a protein in one of these that you mentioned. It strikes me as extraordinarily unlikely that a protein, I mean, a rare event, that a protein would survive the heat of a fall.
Absolutely. It's the only one they've found. It was a lithium, gosh, what was it? It was hemolithinin, I believe is the name of it. And it was an iron lithium ended protein. And it's the only one that they found so far. And I wouldn't say it's super controversial, but there's only been a few papers and they've, it's one of those things where you find one area and then you can't reproduce it. And it was found in the Allende Allende CV3. Carbonaceous chondrite.
That answered the second of my points, which was whether it's been identified. The other is, what are the procedures you take to guarantee it's not the result of contamination after the fall?
It's a really good. So this is certainly not my specialty. My specialty is just diagnostics and basically figuring out where they fit into the taxonomy. But basically, it's a matter of, I would say that from my understanding of it, there is no 100% way for a found meteorite. So the first thing is that they like to use falls. So that means that it's one that they've witnessed a fall and that was recovered almost immediately afterwards. They also oftentimes will take large samplings of the area to identify any indigenous local organic material in order to sort of rule that out as a base. And then now, more and more, now that we've had 2 return samples, that is becoming a non-issue, as we've now got the 2 carbonaceous return missions, and they go to really extreme lengths to keep it as pristine as absolutely possible. And so I think that's really the answer. And so when I think when the amino acids and the prebiotics and the alcohols are really not very controversial. When they start identifying proteins, full proteins, and these much more complex, very, very, very volatile, very fragile molecules, I think we can take it to the bank with these return samples. I think it's the skepticism within these, within meteorites is quite reasonable.
I wasn't trying to be skeptical.
No, well, I think I am. I think it's a fair question. Yes.
Is there an estimate roughly how many meteorites have been found, discovered, and formally cataloged or accounted for?
Many tens of thousands. And I can personally tell you that I've been being on the dealer side of it early on in my career and still unfortunately having to interact with that to some degree. I would say probably only about 0.1% of all the meteorites that are found are actually classified and cataloged and published in the Meteoritical Bulletin. So hundreds and hundreds and hundreds and hundreds of tons.
Do you travel to get these, or do they come to you? Or what is the
Both.
process you go through?
Both. It really depends. If it's a new fall and all things are coming together well, I'll be on a plane and I'll be, in any given part of the world hunting with a bunch of people that are.
And why are so many from Morocco?
It's a good question. I would say it's mainly because of the dry desert. They last there. They don't get weathered away. It's the same reason we're finding more and more in the Atacama Desert. In fact, even older ones, we're finding a lot more paleo meteorites in the Atacama. And then also the Gobi is another really productive area. But I would say it's because for whatever reason, one of the main reasons is historically, there's a very, very strong meteorite community and meteorite hunting industry, really, in Morocco, Mali, Algeria, Mauritania, Libya, the whole area, Africa, Northwest Africa and Northeast Africa. And they know what they're looking for. They know how to recognize them.
Any questions online?
Are there strewn fields in Colorado?
Oh yeah, yeah, definitely. Strewn fields are. I mean, yes, there are, because they have to be a strewn field, but mostly they're more difficult in the United States, generally speaking, because almost all the land is either privately owned or off limits or has very limited access. And so it makes it difficult to establish the strewn field, to go out and sort of, identify exactly where it is. But yeah, there've been quite a few meteorites found in Colorado.
Hey, thank you very much.
Thank you.
Hi, and thank you, Mehmet and everybody else for inviting me here. It's a pleasure to be here. Just 2 introductions. My name is Ed Dauer, as Mehmet said. And the only things that are probably germane about that is, although professionally and by education, I'm a retired lawyer, for most of my adult life, I've been an amateur, very amateur, optical astronomer. And since 1957, I've been a radio amateur. And I think my interest in radio astronomy is probably the child of a marriage of those 2. The second thing I want to introduce is what you see behind me. I hope everybody out there can see it. And that is what you're looking at is called the Allen Array. It was paid for by Paul Allen, who was one of the original founders of Microsoft. It's an array, you can't see the whole thing. It's an array of 42 6-meter radio telescopes located about 200 miles northwest of San Francisco. And the array is managed by SETI, which stands for Search for Extraterrestrial Intelligence, though it's an institute, as I'll mention later, that does a great deal more than just that. Co-managed by SETI and SRI, which is the successor of the Stanford Research Institute. And these are the things I want to be talking about, is radio astronomy and telescopes and arrays. Let's see, spacebar, Doug, there we go. Okay. So this is probably very familiar to everybody in this room. It's the electromagnetic spectrum, which shows the whole continuum that we know from the long wavelength, low frequency radio waves all the way up to gamma and X-rays at the very top. And the reason I have this is actually relevant to a couple of points I want to make. First thing to note is that this is logarithmic, so the whole thing is spread out much more than this. And there's a little narrow piece of it in the middle. I don't have a pointer here, but you can see it on that black line. And that's the entire optical spectrum. It's a fairly small in terms of wavelength. It's from about 400 to 800 nanometers in the whole scheme of things. It's spread out on the bottom just so you can see the colors and the frequencies, but it really occupies that little place just to the above infrared, and infrared, of course, is above the radio spectrum. There's a couple of advantages and disadvantages of optical astronomy and radio astronomy that you can derive some of from this. First, the advantages of optical astronomy, if we have to compare the two, you can see it. When you look at stuff, right? That's what we have evolved to be able to detect. That's a big advantage. The second thing is that as the wavelength gets smaller, the frequency gets higher, the energy of the individual photons also rises. And what that means is that photons of light energy can be captured by and make an impression on a charge coupled device. The energy of a photon at radio frequencies is orders of magnitude, many orders of magnitude, too weak to be able to be captured by CCDs. We need other kinds of techniques. So capturing imagery in optical has that advantage, at least with current technology. The third advantage of optical astronomy is that, as I think everybody knows, the angular resolution of an instrument is a function of both the capture area, the diameter, let's say, of the mirror, if that's what it is, and the wavelength. So the longer the wavelength, if you hold D constant, the worse the angular resolution is. And what that means is at short wavelengths, optical astronomy can image much, much finer, I mean, again, by orders of magnitude, angular resolution than radio astronomy can, although there's a device or a technique that I'll get to in just a moment. And then I guess one of the final advantages of optical astronomy is that there's a lot of stuff you can play with, which, as you'll see, is a little hard when we get into radio astronomy. There's that, but then the typical fully movable radio telescope, one of them I'll show you weighs 17 million pounds. It would have been tough to get it in here. The advantages of the radio spectrum for purposes of astronomical and astrophysical exploration. First, it can detect features that are too cold to emit light. And there's a lot of that out there in the universe that can be seen at radio wavelengths. It doesn't give off light. It's not hot enough. Some functions, synchrotron radiation, for example, doesn't emit light at all. But it does emit radio energy. A third is that there are whole areas of the galaxy. When you look at galaxies, you will see dark clouds of dust and gas, and optical light can't get through those. It's no problem for the proper frequencies of radio energy to get through it, so that in radio astronomy, you can peer right through those barriers to be able to see what would otherwise be hidden behind large areas of cloud and dust. Another is that you can do it during the day, and you can even do it when it's cloudy. Maybe you can even do it when it's rainy. It depends on the frequency you're looking, actually. And that may be, by the way, one of the reasons why England was doing so well with radio astronomy, not with optical. And the drawback, however, of radio astronomy is that there's not an awful lot you can play with. as you'll see in just a minute. Let me get to the next one. You see that. What I want to do, though, is talk about the way in which these two strategies for exploring astronomical phenomena can work hand in hand. And it comes to some extent from the combination of that list of things that I've just given you about the advantages of each. And so I was looking for some of the examples of where radio astronomers and optical astronomers have worked together, and the numbers of those occasions is just vast. But the one that really interested me is something that is really kind of new. It's called fast radio bursts. These are bursts of electromagnetic energy in the radio frequency that are all sub-second. Some of them are millisecond in duration, and yet even those that are milliseconds in duration are indicating some phenomenon that produced all of the power that would have been produced by our sun over a space of 3 days in the space of milliseconds. They are extremely powerful. They're quite rare. There are a few hundred that have occurred. They're hard to track because there seems no rhyme or reason, no pattern of organization of many of them. A few are repeaters, but the repeaters are a small percentage of the total number of FRBs, radio bursts. And they have some very weird kinds of frequency characteristics. The frequency changes in a constant way across most of them, and there's some residual emission that's visible only in the radio spectrum. So there have been two papers that have been published very, very recently, like within the last year, that are probably the state of the art in finding out what these fast radio bursts are. And one of those papers came as a result of a collaboration between these two facilities. One of them is Gran Telescopio Canaris, which is probably the largest optical scope on the planet that also does infrared, does both infrared and above. And the other is NOEMA, which I always forget what it means. I just know that MA stands for millimeter array. I can't remember the rest, but it's a group of radio telescopes in France. Putting those two together, the array, the NOEMA array, located very precisely where some of the bursts were coming from, and then the optical scope was able to image, to the extent it could, that's the right word, could image the immediate environment. And by putting those together, this is kind of a spoiler alert, I suppose, putting those together, it looks as if what fast radio bursts are coming from is highly energetic and highly magnetized neutron stars called magnetars that are embedded in a large plasma bubble, which I don't have a picture of, but it's hard to imagine those anyway. We still don't know what the mechanism is, but at least we have a sense of where they're coming from and what's going on. And that could not have come about without cooperation or collaboration between both of the fields, both radio astronomy and optical astronomy. I want to go back to the electromagnetic spectrum and introduce these two, these very famous devices, just for a moment. Again, the angular resolution is a function of the diameter and the wavelength. And so if you're operating at radio wavelengths, in order to get anywhere near the kind of resolution you can get with optical astronomy, you would have to have a dish that is kilometers wide, literally kilometers. The largest dishes that are being used in radio astronomy are these two. The one on, I'm not sure whether it's your right or your left, the one that's surrounded by the green hills up there is what's called the FAST dish. It's in China. It went online in about the year 2020, so they're still tweaking it. It is 500 meters across. It is not, you can't move that. The way you steer it towards an object is that hanging from all those towers are cables on which can be moved to move the receiver and the feed horns in various places above the dish, which is how it can be aimed. The largest, I think this is true, is so far as I know, the largest fully steerable radio telescope is the one in Green Bank, West Virginia. They both begin with W. Well, Jupiter, Saturn. I can get away with West. I can get away with West Virginia, Wisconsin. Anyways, in West Virginia, it's named the Bird scope. And it is 100 meters across, and this is the one that weighs 17 million pounds for all of the movable parts. And it's an extraordinary instrument, and yet it also is limited in its angular resolution by the fact that when it's dealing with radio wavelengths, the diameter is fairly modest compared to radio wavelengths. It would be quite an instrument at optical. So the angular resolution on these, even on these, is not all that great. Oh, by the way, the FAST telescope is now, I think it's like twice the size of Arecibo, which is now a pile of steel, as you know. And it has something like 3 times the sensitivity. So everybody's waiting to see what this is going to produce. So what do we do about this angular resolution? Well, one of the things we do, and this is why the ATA array is an array, one of the things we do is called aperture synthesis. It's sometimes also called Earth rotation synthesis. And while I'm going to ask Augie to do the mathematics. I can't do the mathematics for you. But what I can tell you is this. If you can imagine 2 radio telescopes pointed at the same point source a few parsecs away, and let's say they're taking this angle, as the Earth moves, the transit time from the source to the antenna that's receiving it would be different in those 2 scopes. And as the Earth moves around like this, it changes and the angle changes. That delay time, or the difference in the arrival time, changes. That creates an interferometer, which, very much like the fringe kind of analyses that is done in optical, has a phase difference, which through absolutely enormous processing kinds of strategies can be turned into, interpreted as angular resolution. And so if you have 2 telescopes that are on we'll call it the baseline, that are 1,000 feet apart, you have the equivalent in angular resolution of a single dish with a 1,000-foot diameter. Now, the sensitivity rises linearly with the sum of all of the dishes, but the aperture rises by the angular resolution rises by thousands and thousands of times. And so the instruments that are really doing radio astronomy are arrays. And the 2 I've got here, one is nearby, the one that looks like a Y, it is a Y, is the one that's in Socorro, New Mexico. It's called the Very Large Array, which is appropriately a good title for it, since each of those arms is 11 miles long. So they can get 2 of these scopes separated by 23 miles, which gives you an enormous baseline and a substantial phase difference that can then be analyzed. The Allen array that I started with is 42 scopes. Originally, it was going to be 305, but Paul Allen got tired of writing checks. So they stopped at 42 scopes, of which 24 have been completely refurbished, but they're all now operating. That one, I'm trying to remember the space that occupies. In any case, that's also an array operating on the same sort of theory, the same strategy. There's also something called a square kilometer array. This actually is an artist's rendering, although there are 2 or 3 of these square kilometer arrays. I can't remember whether that one's the one in South Africa or in Australia, but they are quite literally arrays of square kilometer dimensions. And one of them, which doesn't have dishes, it simply has log periodic antennas sticking up, is going to have 130,000 antennas. You can imagine the processing challenge that creates as the Earth moves and the angles slightly change for all 130,000 of those LPDA antennas. You can also get something called very long baseline interferometry by having 2 scopes on opposite sides of the Earth. That'll give you about a 12,000 kilometer, if I've calculated correctly, baseline. And it can get even longer than that if you have one on Earth and one in space. The problem with doing that has been it's very, very difficult to maintain the alignment of the space telescope, since all of the differences, the physical differences, are so tiny. And so I'm not sure whether any of those are still operating, but so long baseline interferometry is a way in which you can get angular resolutions that actually exceed the angular resolutions possible with optical scopes, not of magnitude, but they do exceed it, and they are in these large arrays. So show and tell, I brought something which I'll call the itty bitty radio telescope. It's sitting right there, and Augie is going to tell you more about that. Ours is made out of a slightly repurposed direct TV dish. He'll tell you about it. But there are entry-level radio telescopes for amateurs that are neither very long baseline arrays nor stuff like that. And there's one in particular, I have not personally built this, though it is my ambition to do so. MIT has online on its, you can find it there on its website, something called the Haystack SRT. SRT stands for Small Radio Telescope. It's 2.3 meters in aperture, which is really manageable. It's what, about 8 feet. And the instructions are right online to do it yourself and to build it out of ordinarily available parts. My ambition is to do that. That kind of a scope, actually you can discern the hydrogen emission line at 21 centimeters, and you can pick out some other of the brighter radio objects in our galaxy and beyond. This little bitty one is sort of just entryway. Just a kind of proof of concept. So, oh, by the way, there was a program run by SETI they called it the end of the small telescope when they discussed these very, very large arrays. And I asked a question at the end. I said, so is there any room left for amateur radio astronomers? And the answer that came back was, you bet. Anything you find, send it to us. We're looking forward to collecting everything we can. So there is room even for those people who can't afford a 17 million pound monster. I would like to, if you allow me to do this, I'd like to take just a minute and talk about SETI, which again is the search for extraterrestrial intelligence, though that name is a narrow slice of what they actually do. I'll read this because I'm not sure if everybody can see it. There's more than 100 scientists and 173 programs in several disciplines: astronomy, astrophysics, exoplanets, planetary exploration, astrobiology, climate, biogeoscience, and they do the search for extraterrestrial intelligence. The search for extraterrestrial intelligence is financed entirely with private money. The rest of the stuff comes from grants from National Science Foundation and from NASA. And they just got another $200 million from one of the founders of Qualcomm, came from his estate, which is what they're doing to refurbish some of these scopes with more modern antennas. So I wanted to mention SETI in particular, because if I can do my own pitch here, a few of us have started what I can only call an affinity group for SETI here in Colorado. SETI runs a number of operations that are available to everybody. They have a newsletter. They put out podcasts and radiocasts. They did until recently something called Movie Night. And one of the ones that I think is most popular is called SETI Talks, which is a monthly program that's broadcast over by Zoom with a Q&A at the end, so that it's possible to engage in conversations with the scientists at SETI, where they're presenting their latest findings going on elsewhere. Very, very active outreach. They even have one called SETI for Families, which is kind of for kids in high school, I guess, or younger. So there's a great deal to do. So a number of us have gotten together, and with the blessings and encouragement of SETI back in California, we've organized a group. It's a very small group so far here in Colorado. And what we plan to do very informally is to get together periodically at one another's home, talk about stuff, go over new items that have been coming to us in various ways, and to have what I guess you would call watch parties. When SETI puts on things like movie night or puts on SETI talks. And one of the things that SETI has given us is kind of front row seats. The last time we did it with one of the SETI talks after the scientists presented what they were talking about, I'm trying to remember what that one was about. That one was searching for planet B, I think, right? It's about exoplanets. Our little group got the first several questions and first recognition. So our relationship with SETI in California is very close, and I want to invite everybody. There's no fee, there's no requirements, there's no anything. Just get in touch with me. That's my email, and we'd be glad to have you aboard. And we will meet from time to time whenever we meet and talk about things of common interest. So Augie is going to finish up, but I don't know if I have time for any questions before he does.
Yeah, you use up more than 10 minutes of your time.
Okay.
Thank you very much.
Okay.
Are there any questions for Ed?
Yes. I'm sorry, I don't know your name, so forgive me for pointing.
Hi, my question is about one of the past uses of the Arecibo radio telescope. Do you know if any of the telescopes have been used to take radar pictures of the misnamed mini moonlet
I
that's
do not
making
know, I'm
one?
afraid.
Okay, I thought maybe somebody would try to catch it with some radar images. Thank you.
Yeah, no, I'm afraid I don't. No more questions? Oh, sorry. Yes, Joe. If it's a hard one, Augie will handle it.
It is not hard. So I heard that the Voyagers were used to help measure distances to other stars. You were talking about long interferometry.
Yeah, long baseline interferometry. I'm sorry, the question again is?
Voyager, the ones that are really far out.
Yeah, yes, I don't know if that's still operating, Joe,
Okay.
as one half of a very long baseline interferometer. I know that they tried that, and one of the problems with those is keeping them stably locked. And in fact, the distances are so tiny when you're doing interferometry, the scopes don't track. They stay fixed and they rely on the Earth's rotation. The reason being that the tracking will induce vibrations that are so small that they'll mess it up. So the precision that's required is really quite extraordinary. So anyway, thank you very much.
One quick question. On your graphic, you showed the 1.4 gigahertz watering hole. What makes that such a quiet spot in the radio spectrum? Why is that a good place to listen?
Or something like that.
The end of it.
But it's called a watering hole. It's called a watering hole for a couple of reasons. One is it is quiet, and so that's where people gather to look. But the other is there's an emission which is it's from the spin flip radiation of neutral hydrogen.
Forward and back.
And so it's a very prominent line, and it's all over the galaxy. And so it's one that you can focus on fairly reliably. So 21 centimeters, I think, is where that is.
We ready to go? Thanks, Ed. I'm Augie Hansen. I'm a ham radio operator. Ed mentioned that Ed is also, that's how we met, in fact. And I've had an interest in optical astronomy since back in the days of Halley's visit. I got an 8-inch Coulter optical telescope, the little 8-inch reflector. And then later on went up to the 13-inch Dobsonian mount, very simple setup. I've never done astrophotography. I depend on Hubble and other places like that, other, systems like that to take the really nice pictures. And I'll just do star hopping and look at the pretty things and try to figure out what's going on. This talk is about a project called the GNU radio project. And forgive me for using the name GNU, pronouncing it that way. It's not the animal. It's actually, GNU is not Unix. Are we seeing everything correct appropriately? Okay. In any case, the GNU radio project is something that started, in fairly recent time. It got started because people who were using Unix, I'm a Bell Labs guy from many years ago, using Unix, but they could not use it outside of the university communities and Bell Labs itself or the Bell system. And so they were developing application programs that ran as if they were on a Unix system, but they weren't. And so GNU stands for GNU's Not Unix. That's all that's going on there. It's a recursive name, obviously invented by some mathematician. It's free open source software. That's the major benefit of it. It provides a lot of signal processing blocks, various other things. The programmers have figured out ways of doing things, developing new algorithms, processing technology to speed up the processing, and you'll see why that's critical here shortly. They're also very heavily involved in defining what software-defined radios are. And in the past, we've used analog radios. Ed and I have had equipment going back, I won't say how many years. We're both 80 years old, so it's a long way back. But they were analog with tubes, transistors, whatever, capacitors. Now it's all integrated technology, very small devices can do lots of miracle things. And there are no knobs, there are no video screens, there's nothing on them. It's just a block with a bunch of stuff inside, and it's programmed by a computer. And that computer does everything, and tuning to a frequency, or scanning a band of frequencies, or looking at a particular signal on one frequency, and then filtering, doing all kinds of processing. And it's all done in software, and basically it's done on a computer. And I'll show you these things in a few minutes here. The uses are widespread, research and development in many fields. Academic areas are using these processing tools, the industrial communities, and even government. Ed mentioned a couple, NASA, the other agencies in the government have been putting money into these projects. Initially, the project with SETI was funded with government money, and then that funding went away eventually. Back in the 90s, I guess it was. And now it's back because some of the agencies say, look, these guys are doing great things. We need their help. But hobbyists are also involved, and I'm one of those hobbyists. And this is the logo that they use. And their basic claim to fame is they have an annual event that they get together, the thing called GRCon. And basically it's to look into the developments that are going on in signal processing, the technology, the algorithms to do the job mathematically. And there's a whole big community of programmers, hundreds of them, working not just in the States, but all around the world. A lot of them in England, a lot of them here in the States, but also pretty much spread around the world. And it's a very active community. Come on, you're supposed to go down. Well, why is it not moving? Spacebar? Okay, we'll go there. I think it is, yeah. Yeah, just that. I just wanted to mention this. Ed gave me 10 seconds on the SETI because he's already talked about it. They're having a happy birthday later on this month for 40 years worth of activity. They're basically 1984 is when they got started. So George Orwell's favorite year. And if you have the money and the time, go to Menlo Park, California, and have a wonderful time. Radio telescope. Let's start out with components. The thing that I want to show you today basically is based on what I'm showing you here. This is how we would set up an amateur radio astronomy telescope system. And it involves three parts, basically: the antenna, the software-defined radio, and the computer that runs the radio. There are several different types of antennas that I'm showing here. The one that's got the long, skinny bar through the middle and the loop at the back, that's a Yagi style antenna. The little short elements up front are directors. The one in the back is a reflector, and the loop is the driven element, it's called. It's driven if you're transmitting, it's receiving when the signals are coming to you, and the direction of travel is in the direction of the short elements there. The other one at the top is a log periodic dipole array. It's distinguished from the Augie in that it covers a much wider bandwidth. The Augie may have a peak of a strong signal where it has a lot of gain, but as you move away from that frequency, it falls off. And when you get 3 dB down, which is the half power point, you're basically at the end of the usable bandwidth of that antenna. The log periodic dipole array can go 3 octaves of frequency change, even more, but it's a little difficult to do that well. But it has consistent gain, relatively speaking, not perfect, but very consistent across the passband all the way from one end to the other. And it has front to back, meaning it's pointing in one direction, picking up signals and rejecting anything coming from the backside or from the sides. And so that's a device that's being used now in some of the telescopes. And the ones that Ed mentioned, the 42 telescopes, 24, you say, have been updated with the new feed system using LPDA type receiving antennas rather than original dipoles. And then that third one that's showing there actually has a little LPDA, that triangular shape at the front is the pickup. That's where the antenna is that's receiving the signals. Signals are coming in and reflecting off that back panel. And this one's called a parabolic grid. Notice it's just parallel wires. It's all metal. But it doesn't have to be a plate. This one over here is a plate. It doesn't have to be that way when you get to lower frequencies. This one is for a lower frequency, and so it can use that grid. This antenna has to be this way because the higher frequencies have much shorter wavelengths, and so the wire spacing would be so close, it would be difficult to do, and it's better just to make a flat panel. Oh, I'm sorry, I shouldn't go back one. The software-defined radio is another piece. I have one right here. This one is a different one. This one's made in, I believe this one's from England. SDR receiver, it's called, software-defined receiver. Well, software-defined radio receiver is what the SDR stands for. And that's the thing that's being programmed by software that's running on a computer. And as you can see, there's an image showing a computer screen. I'll be showing you on here what that looks like. This is the kind of a dish that we're going to use in this demonstration. And that microphone is over here. Okay. And you're going to have to move the camera at some point here. What I'm going to show you is this dish is the DirecTV. And basically there's a dipole antenna right up here in the front. This white area is where the antenna is actually located. And then right behind it is this block. It's called an LNB. That's the low noise block. And in there are 2 components for this particular antenna. The reason for it is the signals coming in have to be amplified. The low noise amplifier is boosting the signal up to a higher level so that it can transfer signals through coaxial cables going some distance. And coaxial cables tend to be lossy. You want to put as much gain as you can up front so that the signals passing through get to the end with good signal clarity. Also inside this one, because of the nature of the antenna, there's a down converter. There's a local oscillator in there that's beat together with the incoming signals. The oscillator runs at 10.750 gigahertz, and it takes signals that are in the range of 11.7 to 12.5 gigahertz, very short wavelengths, and it converts them down to that's the KU band, by the way. It converts those signals down to a lower frequency, which is in the L band, somewhere between a little bit below 1 gigahertz and up to about 2 gigahertz is where that goes. And so those signals end up coming down here. Is there a question? All right. In any case, that is putting the signal out. And then the next step in the process is to go through an SDR radio. And if I tap this, this is an example of the one I'm using here. This is from a company called SDR Play. And this one is called the RSP-DX. And it has an R2 designation after it, which means it's a revision number 2, which brings it up to date with the most modern technology available to us. And it's just a little tiny box. There's not much in here. At least it doesn't look like there is. But it turns out there's a lot of integrated circuits in here, including DSP chips for digital signal processing, the radio amplifiers and mixers and other features of the radio. But all of that is controlled through this USB cable here going to the computer. And also the power for this little guy comes from the computer. Just 5 volts is what runs this thing. And so that's taking in signals, and then it's producing okay, my laptop had gone to sleep. But in any case, that is producing signals that are coming in on this wire. This is going into antenna port 1. There are 3 antenna ports on this particular SDR device, and they can be used for different antennas. And one of the things that antenna that I called the Yagi that I showed you, think of this. It has the ability to adjust elevation and azimuth in the same way that a Dobsonian mount, let's say for a reflector telescope would do. You can aim it up, down, sideways, and it sees a fairly narrow stretch of sky in the radio spectrum. You could take that Yagi that I showed you and strap it on here, put a low noise amplifier on it, feed it in this other channel here, and use that like a spotting scope on a big reflector telescope. You could use the same kind of technology, but you're working at lower frequencies. And then the third step in the process is the computer. Whoops, why did it go backwards? There we go. The third part is the computer system. And typically a laptop like this will do the job. I'll show you the pictures on screen because it'll be easy to see. This laptop isn't plugged in, so I can't show you. And what's on the screen right now is basically dark anyway. But anyway, this is the program on here. It's called SDR Connect, which is what I'm referring to in that last bullet. And that's a program that's been put together by SDR Play, the company that sells this piece of hardware. This little guy here costs about $240, I think is what I paid for it. You can buy a thumb drive sized device. It's called a dongle, plug it into the computer, and it does the same job, not over quite the same frequency range, only up to 1 gigahertz. But if you're not going to go higher than that, then you could use this SDR radio, just a little plug-in in the side of your computer and have the same basic features. But this one has 3 inputs. It has another antenna input, which is a BNC rather than SMA, makes it convenient to hook up different kinds of cable systems. But anyway, that's basically it on the 3 components. And let's carry this a step forward. And this is what the screen looks like. I'll go over here to this microphone now. This is what the screen looks like. In the upper left-hand corner in your view is a spectrum scope. And what you're seeing there is a filtered waveform. And I'm not able to show you anything in here tonight because that's a direct TV dish. And its primary purpose is picking up satellites to show you video and audio. And it does a very good job of that. It doesn't do a very good job of anything else. I'm not recommending that as what you would do if you want to be a radio astronomer. I'd go for that parabolic grid reflector, which picks up much lower frequencies. It has an antenna at the focal point, at the prime focus, which is receiving signals around 1.42 gigahertz, the watering hole that you saw in Ed's slide. That's where we can actually look through what I call the cosmic schmutz and see things electronically with electromagnetic waves that you cannot see in an optical telescope. In fact, you can look into areas where there are black holes hidden in dust and gas fields and get to see a lot more stuff. Down below that is a thing called a waterfall. And the reason for that is you might see a spike or two or some signal in the spectrograph up top, but it may come and go very quickly. The waterfall traces it for the next 5 or 10 seconds if it pops on the screen, you'll see it go and go away, but on the waterfall, it stays there in your view as it travels down and finally goes off the bottom of the screen. And then there's places, there's a lot of buttons for controlling things. I have it set on the keypad where you can enter the frequency you want to tune to. And you can use your mouse to move around. And that line that's showing there, that vertical line, is where I had set my point. And when I keyed in the frequency, of 900 and some, 950 or 980. I'm not sure what I did there. Yeah, 980 megahertz. That's what that line represents. And then the spectrum scope shows you plus or minus some distance, and you can change that bandwidth. You can look at a couple of kilohertz, or you can look at a couple of megahertz or 100 megahertz by setting appropriate controls here. So this is a basic radio telescope. It's a fully functional radio telescope, and something that you can build for, I think, what'd you say, what, 50 or 60 bucks for the dish, a couple of $100 maximum, I'd say, for the SDR radio. And then you probably have a dozen laptops hanging around somewhere, don't you? Just use one of them. And by the way, that software SDR Connect runs on Linux, on several different versions of Linux, including Ubuntu. It can also run on Mac OS and on Windows. So you have some flexibility there depending on what kind of computer hardware you have. All right. This is a notice that came out in 2020, September, of the joint SETI Institute and GNU Radio project. The people at SETI realized that the GNU folks were developing some really interesting hardware and software, and they've been using that association now for several years. They're continuing to do signal processing work that was already underway at the ATA. That's the one that's at Hat Creek, not too far up northwest of San Francisco, I guess it is. And they're updating some of the older stuff. I call it one-off types. In the old days, if you wanted to change the mechanism that you were using to demodulate signals that you were getting from somewhere in space, wherever it was from, you had to have a custom-made piece of hardware that would do that job. And to do a different job, you had to pull that hardware out, put in a new piece of hardware. Now you don't do that anymore. The SDR radio, you just key in a few strokes and bang, off you go. You've got a new modulation scheme, a new processing algorithm, whatever it is you need. And so it's a very helpful collaboration that these two have. Data acquisition, you have to understand the problem here. Continuous operation, you can do it day, night, any time of the year, doesn't care what the weather is. And there are, at the ATA, 42 telescopes. They can be used either individually, singly, or in pairs, or in groups. You might have one group focused on one part of the universe while another group is focused on some other part. And so there's a big problem here. They slice the spectrum into 1 hertz wide spectrum slices. And there are millions of them because they're looking at a very wide range of frequencies, mostly in the gigahertz range, but also down lower too, now near the watering hole, 1.42 gigahertz, and even lower than that. So at each slice, there's up to a couple of thousand cycles per second, samples per second. If you're sampling that many samples on just 1 hertz, and you've got millions of hertz, you got a lot of data coming in. And there are many more bytes added to it because each of those samples has to keep track of where it is, which scope am I on, where is it physically located, longitude, latitude, what time of day was this taken, what millisecond or nanosecond was this taken at? And that data has to be stored quickly. And so it's like I show there, trying to drink water out of a fire hose. The issue is primarily massive speed, very high speed and massive data storage. It's very tricky to do this job because you have to get the information out and store it very rapidly. And the way they do this, they can't really wire the stuff back in some circumstances. I'll show you in a moment what I'm getting at here. The important thing about it is when you store this information, somebody's going to need access to it. There are hundreds of projects going on at any given time, and each needs different things. They may need samples from a particular frequency range, or they may just need samples every couple of seconds, or samples every couple of minutes, or whatever it is. You need to make that information shareable in such a way that anybody can get to it. Well, I've already talked a little bit about the data acquisition part. Data storage can be either local or in the cloud, but that local storage means a couple of different things. There may be some central facility within the Hat Creek ATA facility where all this data is collected, but it's actually being stored at the individual telescopes and then collected, brought together, and then stored. And that's why each one has to keep track of things accurately. And what is it that they're using it? A maser?
Atomic clock, maser of the atomic clock.
Yeah, okay. And that's how they synchronize everything. All those data samples are synchronized by this clock mechanism, which is very accurate. And then they can bring this stuff together. The access to this data after the fact is done through a thing called the VNC, which is a virtual network computing system. And it's called commensal access. That's kind of like symbiotic relationships. The whale has all kinds of critters on its, on its back, and they survive by eating skin cells and whatever, but they do no harm to the host. And in this case, the host is the VNC, and each organization can go and extract what it needs from there without doing any harm or any benefit, for that matter, to any other user of the system. That's the important process here. The data processing that's done by those individual organizations, they do their own triage, deciding what pieces they need and getting what they need to do to process that information successfully. That's being done by what are called blocks. And this is the last slide that you have to worry about, remembering this, because I'm going to give you a test when I'm done here. The coding is mostly done, by the way, in Python, which is an interpreted language. So it's not really fast. It's fast enough to do management type activities, organizing data, putting things where they need to go. But the high-speed stuff, what it's called the work function, is done by C++ programming, usually. There are some other languages being used too, depending on who's doing the programming and what they know best. But anyway, those are the primary languages. The work functions are the things that are done in the middle of these blocks, and each block has highly defined inputs and outputs. And any of you here Unix users or Linux users, okay, you understand if any of you use the console rather than the pretty GUIs. If you use the console, you're familiar with the process called pipelining, where you have a function in a little application, and you can pipe these things together and get a result. For example, you have a list of thousands of names, and you want to get rid of duplicates, and you want to organize it alphabetically. Well, first thing, organize it alphabetically, and then all of the duplicates will be next to each other if there are any. And then you run that through a program called unique, and that gets rid of everything except the one that you want to keep. And then you end up with a list of just the names you wanted, only one time, alphabetically organized. Well, the same thing is going on here. These are pipelines. They call it a flow graph in this example. And basically, you just have to tie outputs to inputs and use the functions that you need, fast Fourier transform, for example, or math functions, whatever it is you need, pipe it together, and you can process any data any way you need to do it. A couple of sources you can go to, and I've listed a couple of websites here, one for SETI and two for the GNU Radio project. And then there's one that is the combined the collaboration. There was a program put together, a blog, I guess it was, by Seth Shostak and a number of other individuals who were involved in various aspects of the project. And they were showing how they were coordinating their efforts. And then there's an example for pipelining. For those of you who want to dig a little bit deeper, if you're interested in that sort of thing, there's an example that shows how pipelining is done using these flow charts and the blocks. Any questions? Yes. You want the microphone?
If I were to build one of these $300-ish system you're talking about, how would I know where to point it? How would I know where to point it? I mean, I obviously know nothing about.
How do you know where to point? Yeah.
Right.
This particular dish over here is designed for a purpose, and that is to hook up with the satellites that are in geosynchronous locations. And there's a defined offset from any terrestrial location. Fortunately, they happen to be a little bit north of the equator and almost due south. And so you can get in that. Go ahead, Ed.
Radio astronomy uses the same system as optical astronomy. And there's a collection at 3C, I think C is for Cambridge. But there's a collection of radio sources that have published RA and DEC figures. So you can do the same thing. Although with something that small, you just point. And one guy built one of these and said he thought he was seeing Cygnus A, but it turned out to be his neighbor's dishwasher. It's not very accurate.
In any case, the other kinds of things you might be looking for, though, and by the way, I'd recommend for this kind of a setup, what you really want is probably what's called an L-band antenna, which is much bigger. It has something on the order of 6 to 8 feet diameter or at least width on that parabolic grid. And then the LPDA antenna sitting out front at the prime focus. And that's in the about 750 megahertz to about the 2 gigahertz range is where those L-band signals are. And that's where the watering hole is at 1.42 gigahertz, plus or minus a little bit. And that's where you look for the hydrogen line. And you can look through, that's when I say you're looking through the cosmic schmutz. What you're looking for is a way to get at the black holes and various other things. And you can use your optical astronomy maps to know where to look and then aim it. But you'd have to set this thing up. And by the way, this is just like a Dobsonian mount, as I say, just LAS kind of stuff, but manual. In order to do the job right, if you have to have this thing outside where you can actually get some signals, you're not going to get them in here. And you have to have some way to control azimuth and elevation to point at those objects. There are very nice pieces of software that are available for free on the net that can run on most of the operating systems and do a very nice job of telling you where to point.
Just a quick question, slightly off, but did they ever determine what the origin was of the WOW signal?
No, it's a mystery. They want to know what the origin of the WOW signal is, and there was an event that happened a while back, and somebody wrote "wow" on the paper. There was a chart recorder, and that's all we know about it. And it never repeated, I don't think, as far as I know. And so it could have been anything. It could have been an explosion in space. Somebody doesn't, if you're not looking at it at the time, you have no idea where it came from. We still don't know. Okay, that's it. All right. Oh, yeah.
Every time I look at a radio telescope, it looks like the receiver is offset from where the prime focus would be. Is that?
Yeah, there are a couple of different kinds of telescopes. Are you familiar with the Cassegrain type? Yeah, that would put some object in the middle and obscure part of your view. By using this offset arrangement like this, and then the actual the signals coming in get reflected at an angle, that thing doesn't obscure any portion of that dish from where the signals coming in are being received, or maybe there's just a little infringing right near the edge there, but that's to move that stuff out of the center. And there are other radio telescopes. This is fine for a small telescope, but Ed was telling me you got to watch out when you go to the bigger telescopes. The prime focus is way the hell up there. How are you going to get to it, And in Arecibo, you had to walk on a catwalk and get out there in the building in the middle where they had the prime focus. Not an easy thing to do. And so that's why this thing is set up the way it is here. Okay. All right.
Thank you.
All right. Thank you.
Thank you. So you have seen several show and tells this evening. I'm going to finish it with a rather simple one and very quick. This is about the comet that we observed in the last month or so. Some people called it once in a lifetime. Some people called it once in a century, but actually it is once in 80,000 years. It is Tsuchinshan-ATLAS comet. most of the comets, as you know, come from Oort cloud, and this one as well. And NASA calculated it for some reason as 80,000 year orbit. Of course, we weren't around. The civilization wasn't around at that time last time, and we may not be around next time. But it was one of the brightest comets in the last 27 years. And it was the closest to us about a month ago, 12th of October. And I saw some figures like 60 million miles from us. Southern Hemisphere was the best place to observe it, but lots of people on the Northern Hemisphere, luckily for us, we have observed it as well. The head of the comet was about 130,000 miles, which is about 15 times the size of Earth. So it's quite huge. And the tail was about 18 million miles. It was first discovered by the Chinese Purple Mountain Observatory called Tsuchinshan, but it was considered at that time or thought to be an asteroid. A few months later, actually a month later, in South Africa, the Asteroid Terrestrial Impact Alert System, which is ATLAS, confirmed that it was a comet. So that's how the name of Tsuchinshan-ATLAS came about. The orbit of this comet is as shown here. It is today, it's not very clear, but it is leaving us way past Mars on the way to Jupiter orbit. It was closest to Sun about 30 million miles. And that is somewhat critical, as you'll see a bit later. I have several pictures of this comet taken from different parts of the Earth to give you a perspective. This is from the Southern Hemisphere, Australia, one of the earliest pictures that we have. This is from Victoria, Australia. You can see how huge the tail is. This was actually taken in Egypt, and compilation of 300 pictures shows in very good detail how the comet looked, quite impressive. This one also taken in Egypt, and this actually is the oldest pyramid in Egypt, about, I think, 2600 BC. Of course, it was nothing was around last time this comet came around. This one is an interesting image of the comet taken in Arizona. Includes a meteor at the corner, as you can see at the top left corner. That meteor is from the Orionite meteor shower. And these meteors are the remnants of the Halley Comet, as you may know. So this image includes something of the Halley Comet, as well as the Tsuchinshan-ATLAS comet, the two comets being captured, or the remnants of one, and the actual other comet captured on the same image. And there are several such images on internet. This one was one of the earliest pictures that I have seen in the early morning hours in California, as just before the sunset. By the way, we have seen in North America about 45 minutes after sunset in the evenings. But this picture is one of the early pictures just before the sunrise. This picture, also taken in California, And the interesting thing about this picture of the comet is you can see Venus at the bottom, as well as the Milky Way on the left. So it actually captures a planet, Venus, comet, and the Milky Way. This one is one of the scariest pictures that I have seen. It is almost like a rocket coming down. This is an Egyptian picture, and it's quite colorful and one of my favorites. This one is interesting because it includes, if you can see it, anti-tail at the bottom. Anti-tail is not an optical illusion, as some people may think, but it is actually dust particles between the comet and the sun. And it is briefly seen. It is not, you cannot capture it anytime. And this is because the Earth is passing through the comet's orbital plane. And there is a scientific explanation for this. And it is through dust particles from the comet. This one also shows the anti-tail. This is also taken in North America, Arizona, and you can see how huge the tail is, and the anti-tail is right in front of it, and it's very visible in this case. This one taken in Tucson. I liked it because of the picture, I guess. This is one of ours. Ron took this picture from his house. I don't know whether Ron is online or not, using his iPhone. And it was on October 14. And this is what my wife took a couple of days later with her iPhone. So you don't really need sophisticated SLR or telescope. Actually, we could see it with naked eye or with binoculars. It was relatively easy to look at it or see it. I have one last chart on comets. This is a comet that happened to approach us last month, called Halloween Comet. Interestingly, this crashed on the sun. It broke apart, evaporated, and hit the sun or atmosphere of the sun. The reason for that is it was a comet, type of comet called sun glazers. These are the comets that approach within 1 million miles of the sun. So if you are that close, sun captures you. And the comet that I talked about was 30 million miles from the sun. So he survived, they survived. But this one didn't. And the European Space Agency and NASA's mission called Solar and Heliosphere Observatory captured these two images of how the comet hit the sun. So I have Jim Rasmussen mentioned here because he was the one I approached first to give this presentation. He is actually one of our comet experts in our DAS, but he wasn't able to, but he helped me with this. So I should acknowledge that here. And he also gave me a bunch of resources, some of which you all know, of course, Space Weather, Starry Night program, and Stellarium. But also this Dutch website specific for the comments is quite useful. So that's all I have. Are there any questions on the comment? Well,
when's the next one coming around?
Well, actually, there are several comments. I believe there is one coming early next year. I don't have the specifics, but the actually this Astro-Vambutanen.nl lists all the comets that are approaching the solar system, and it's almost like one a month or once every 2 months, but not all of them are visible. So this particular one that I talked about was one of the brightest in the last 20-something years. That's why it was interesting. But I suggest if you are interested in comets, that particular Dutch website would be the source to look at. Okay, thank you.